Okay, now let's talk about what work means. So, in terms of kinetic energy is how much energy is needed to keep an object moving. We can look at work as the change in kinetic energy, and that's called the work energy theorem. But if that means if kinetic energy decreases, we're losing energy from the system, and that's called negative work. Okay, and if kinetic energy increases, if the object speeds up, that means additional energy needed to be added to the system, and that's called positive work. Okay, and we look at work as done on the object itself. So we define a particular object, that'll be our reference point, and if energy is transferred to the object, that's positive work done on the object, and if the object is losing energy, that's negative work done on the object. Okay, um, so the object has to move in order for work to be done. Okay, so if you're just pushing against a wall, that's not work. Okay, um, even though I know you might go to work and not do anything at your job, but in this case, for this definition of work, the object has to be moved, energy has to be transferred. Okay. And so we're going to introduce the concept of the dot product. So the dot product allows us to say we will only work or look at parallel components. Okay, and this is the work theorem. So work is defined as the dot product of force and displacement. Force and displacement. Okay. Um, and in this case, we can use force as a constant, but we will look at force being variable. In that case, we need calculus. So we also look at a rigid object. Okay, so a very simple case to start with. Okay, so it's how much force is being applied to an object, and that force, how much of that force actually causes that object to move. Okay, so this is not just a multiplication sign, this is the dot product. And so you could apply a force at an angle, and it's only work is only considered to be done as that component of the work that actually causes the object to move. So if the object moves parallel to the ground, then we only look at the force component that's parallel to that. Right? But this is a very important equation. Know this equation. Work is equal to force times displacement. Force times change in x. We'll even look at it as distance later when we talk about friction. Okay, so let's look at this one, for instance. Chaz, you got a new job. You're a room sweeper, and you're pushing on a broom, shown in this figure. It's very funny, Chaz. You're using 15 newtons of force to move the broom 3 meters, okay, and in this direction. Okay, so you're pushing, it moves 3 meters. How much work is done on the broom? Well, you might just think it would be 15 times 3, but it's not, okay? If you were to draw a force diagram here onto the broom, so we'll say that this is where the broom is going to be, and you're pushing down onto that broom right there. Okay, so here's your broom. You're pushing down onto it. I don't care about the normal force and gravity, so those are just canceling out. They're not causing the object to move. But here's your applied force. And the angle right here is 60. It's just the vertical angle. Okay. Pushing down is not pushing down into the wall. In fact, the normal force is just increasing to compensate for that. Okay. So if the object moves in this direction, then this, when we care about work, how much energy is basically being added to the system, I only care about the energy that causes it to move. Okay, so if we look at force and the dot product of displacement, there's all these crazy formulas you can do, but if you just think about as only forces that are acting in the same direction as displacement, parallel to displacement, then it'll be so much easier for you, okay? So if we look at the parallel component here, this would just be applied force cosine of 60. And so this would just be 15 times the cosine of 60, and then it moved 3 meters. and that'll give us a Newton meter. And so that's how much energy he added to the system to get it to move. Okay, and so what is cosine of 60? It is, cosine of 60 is 1/2? Yes. Okay. So this is just 1/2. So 15 halves times 3 would be 45 halves, which is 22.5. It's 22.5 Newton meters. And that we can now write as a joule. But you can think about this, if I wanted it to move it 1 meter, it was 22.5 newtons per times 1 meter. Okay, and then that's a joule. That's how much energy needed to add to the system. Okay, so big takeaway here is make sure you only look at the parallel. So same thing here. If you have a 3.5 kilogram block and it's drawn at a constant speed, 4 meters along the horizontal floor by a rope exerting an 8 Newton force at an angle of 15 degrees above the horizontal, compute the work done by the rope. So we're actually going to do this problem tomorrow. You can see if you can do this one today. But when you think about the work done, you have to think this is 15 degrees here. Okay? If you're not pulling the object up off the ground, there's no work done by the vertical component. The only work done should be parallel to displacements. And we'll work on this problem tomorrow. So let's look at what's called the work kinetic energy theorem. Okay, so it's kind of a circular definition, but it's really just what we've defined to be work by our definition of work and what we define to be kinetic energy. But the work kinetic energy theorem states that change in kinetic energy is actually equal to work. So if your speed increases, so your kf should be larger then. If your speed increases, then you're adding energy to the system. So you've done work onto the system. If your speed decreases, this would be a negative value, and you've taken energy away from the system. Okay. Don't worry about this so much. We'll rewrite this later. So for instance, let's say the kinetic energy of a particle is initially 5 joules. Okay, so perhaps it has a mass of 2 and it's moving at square root of 5 meters per second. Okay, so anyway, its initial energy, it has 5 joules to keep it moving. Okay, so if you add 2 joules of energy, it'll move faster, and its final kinetic energy would now be 7 joules. If you take away 2 joules, it's going to slow down and now be 3 joules. Okay, so it's the change in kinetic energy. It's simple enough. And so let's actually, tomorrow we're actually going to prove that kinetic energy is equal to 1/2 mv squared based off of the concept that work is equal to the change in kinetic energy. It's kf minus k. So let's answer this question real quick. A particle moves along an x-axis. Does the kinetic energy of the particle increase, decrease, or remain the same if the particle's velocity changes from, let's look at part A, -3 meters per second to -2. So the initial is -3, and the final is -2. You can pause the video if you want and then argue if that makes you happy. So let's look at this. Okay, does the kinetic energy increase or decrease? Okay, so the change in kinetic energy is really what we're looking for here. It's really the work. So it should just be 1/2 times the mass, Vf squared minus Vi squared. Okay, and if I had just done the initial kinetic energy, or the individual kinetic energy is just factored out 1/2 m, because the mass of the object's not changing. So this would just be 1/2 times the mass. It would be -3, and when I square that, it becomes +3. The negative just means direction in this case, right? So this is going to be a positive value. That's all I need to know. Speed increased, therefore kinetic energy increased. That's all you need to know. The speed increases in the same direction. really not even in the same direction. If the speed increases, you're adding energy to the system. How about from -2 to 2? Okay, so all you've done is change direction, but your speed hasn't changed. So following this same logic, because we squared the negative, it won't matter. So this should have a change of kinetic energy of 0. So what does that mean? That means you haven't done any work on the system over that time interval. Okay, so you might have done work to get it to change speed at intermediate sections, instantaneous. Instantaneous added energy, but overall, if you look over that time interval, the network was 0. You had to slow it down, then you added it back, or then you had to add energy to speed it back up. Okay, so that's the second question. This one, the work would be 0, and in this one, an added energy, the work would be positive. Okay, let's look at one more thing, calculus. All right, so again, let's define work as force times displacement. I'm going to write this, and this is the dot product, which means it has to be parallel. So if we look at a graph, let's say it's a variable force, like this. I know this graph is horrible, okay? But this is force versus displacement graph. We've looked at force versus time graphs before. This is force versus displacement, okay? Now if you multiply these, that's the same as finding the area of a rectangle, length times width. So if we make infinitely many rectangles and then find the limit as the distance between each rectangle, or the width of each rectangle basically decreases to 0, so it'll be the limit as change of x approaches 0, then what we've just done is really done a Riemann sum and defined the interval. So work can be defined as if you have a force versus displacement graph, you integrate that with respect to x. You integrate your force graph with respect to position with change in x. And if you add bounds to this, it'll be your initial position and your final position. And so if we find the area under a curve of a force position graph, it's the amount of energy that's either been added or taken away from the system during that displacement period. Okay. And if it is multi-dimensional, just like we've always done, you work this out per dimension. Each dimension should act individually of each other, and then the total work, since this is energy, if you want to see the total amount of energy added to the system or the total amount taken away, you add them all up. You add how much work was done in the x component, how much work was done in the y, and if there is a z component, added up in the z component. Okay? And for each one, kinetic energy still applies. You can do the kinetic energy in the x direction, in the y direction, or the overall net direction, whatever velocity is in the speed, I suppose. Okay, so what can we take away from everything we've done today? That would be kinetic energy is defined as 1/2 mv squared. Energy is in the units of a joule, which is a Newton meter. So think about how much energy is added to a system would be joules would be positive. If you take away energy from a system, it would be negative. In terms of kinetic energy, it speeds up, it slows down, and we can also define it always with a dot product. The dot product is important. That always means that they must act. We only look at the forces that act in the same direction, parallel to displacement. And work is defined as the change in kinetic energy. Okay, so how much energy was required to get the object moving at a certain instantaneous speed, whether you had to add energy or take energy out of the system. Okay, so we will discuss this more in depth tomorrow and then actually start working on problems. Have fun playing your Geo whatever game. So